In this problem, it's a proportion problem where we're comparing proportions from two cities here. They've taken a sample from Seattle and a sample from Minneapolis to determine the proportion of users with college degrees in a particular age group. And we want to create a 99% confidence interval estimate for the difference between the two populations. Okay, so the first thing we need to do, or there's several things we need to do to get to the point where we can use that equation here at the bottom of the screen. And so what we want to do is determine our p-bar for Seattle and p-bar for Minneapolis, and to do that we would just take, so for Seattle we would take 66 over 200, and for Minneapolis we would take 63 over 180. Okay, so these values in the table right here. Okay, and to do that, so in that case, so p-bar for Seattle, here we're looking for this right here, is 0.33. Those are threes if you can't tell. I can barely read them myself. And for Minneapolis it's 0.35. Okay, so those are our two proportions from our samples. So 63 out of 180 is 35%, right? Okay. So then we also need the critical value, because you remember for proportions our general formula is point estimate plus or minus critical value times standard error. Okay, so that's the general one. So here we've got, we need our critical value, and so we're looking for a 99% confidence interval estimate. So for that we would use the standard normal table for proportions. We're always using the z values here, and we're looking for half of 99 in the body of the table, and so right between there we find almost 49. It'd be 0.495 would be half of 99. So we find two values that are equally split. So we would then say for z, for our critical value, is going to be equal to 2.575. Right, just splitting the difference between 2.57 and 2.58. Okay, so now we have this portion. We'd have the known values there, so we'd have 0.33 minus 0.35, so we're going to have a negative 0.02 plus or minus 2.575, and then we got to find the answer, or the value here for all the numbers here under the square root. So we've got the beginning of that right now, so we'll get that value. We'll populate that now. So for this formula here, we would have, for this portion of it here, we'll be working on, so we have 0.33 times 1 minus 0.3, so 0.67, and that's over N1 for Seattle, that's going to be 200. And then we have plus, and for Minneapolis we have 0.35 minus 0.65 over 180. Okay, and all of this is going to be, we'll take the square root of all of that. So what we get then is we get the square root then of 0.0011 plus 0.0013, and all of that eventually becomes 0.0486. 0486. Okay, so this is our formula. We've got a negative 0.02 plus or minus the critical value 2.575 times 0.0486. Okay, so again, when we think about a confidence interval estimate, what we're doing, so we've taken the difference between the two is negative 0.02, right? So we've got a 2% difference between the two proportions that we sampled, but because it's a sample, we know there's going to be sampling error, and so the confidence interval estimate will give us a range of possible values that says the true difference between the populations is somewhere between these two values, the upper and lower limit that we'll calculate. Okay, so that's what we're doing. So we've taken a sample. In this case, Seattle was 2% lower than Minneapolis, but now we're going to add this margin of error around that to create our confidence interval estimate. And so what we get then is we get a negative 0.02 plus or minus, and our margin of error is going to be 0.1252. Okay, so about 12% difference. Okay, so what we end up with then for our confidence interval estimate is we get 10.5 or 0.105, right? So 10.5%, or negative 14.52. Okay, so we've added and subtracted from negative 0.02 this 12%. So negative 2% minus 12% is this 14.52, and then 10.5 on the other end with the negative 0.02 right in the middle, right? So this is exactly in the middle, and we're adding that margin of error on either side. So what we would see then here, what we would conclude is that there's we had a difference in our sample result of 2%, right, as we would expect, because there is a sampling error, but it's not such a large difference that we can say with 99% confidence that Seattle is always less than Minneapolis, right? If that were the case, we would not cross zero in our confidence interval estimate. In this case, we go from negative on this end to positive on this end, so we know zero is in there somewhere. And what we would conclude from that is, well, yeah, there's a difference here in our sample, but we can't say for sure that Seattle is always less than Minneapolis. If our margin of error were 1%, for example, we would be able to say that because we wouldn't cross zero. But in this case, with our margin of error, again, a 99% confidence interval, we would not conclude that one is always larger or smaller than the other. Okay, so now that's the first part of this problem, and we'll move to the second part now, the hypothesis test. Okay, and so again, if we just think about this a little bit, we would say, well, if we didn't find a difference between the two in our confidence interval estimate, all right, that is, we had zero contained within the interval. A hypothesis test, at least using the same or corresponding significance levels or alpha values, we would find the same thing, or we should. It should be consistent. Okay, so that's what we should sort of expect going in. And so let's look at this. So based on the age group sampled in the two cities, can we conclude there is a difference between the population proportions? And so again, so this one, is there a difference? And if we think, in the class we always draw our normal distribution, or draw what we're looking for here. We've got these, in this case, if I look at the hypothesis statements here, one is that they're equal in the null, and the alternative is that they're not equal. So one is high, one might be higher, or might be lower. So we're going to have rejection regions on both ends, right? So we split our alpha value in half, and we get 0.005 in either end, and that corresponds to the same critical value z of 2.575. So here we would have 2.575 here and negative 2.575 here. And we're saying, so if it falls into either of those rejection regions, our result, then we will be able to conclude that there is a difference. But if it falls somewhere outside or between those two cutoff points, then we would say, well, no, we can't conclude that there's a difference, right? Even though we might get a difference, or we would expect to get a difference in a sample, they're not going to be exactly the same. But that's where the point where we're starting from. So in this case, we need to do a few different things. We need to find, if you recall, so earlier we got our p-bar for here was 0.33 for Seattle and 0.35 for Minneapolis. And then the way that we get for an estimate for our pooled population proportion, just plain old p-bar rather than p-bar 1 or p-bar 2, we would just add the two x values here, 66 and 63, so we get 129, and then we add the two n values and we get 380. Okay, so if we do the same thing then, so p-bar for the population is going to be 129 out of 380, which is 0.34. Okay, so that's the value we're going to use for that, and that comes into play here in the denominator of this equation right here. All right, and that we'll be moving on to that in a moment. First we've got to get our decision rule. So what will we decide, or how will we decide our result here on that? So we will say then our decision rule then, and I'm referring back to this up here, so we're just going to put that into a sentence. We're going to say if our test statistic z is greater than 2.575 or less than negative 2.575, we will reject the null. Otherwise, do not reject. Okay? So if our test stat is less than z of alpha equals negative 2.575 or greater than 2.575, reject the null. Otherwise, do not reject. Okay? All right. So that's just as we've done in class, it's kind of the standard format that we've been using for how to state our decision rule. So we need to know that going in. We've taken our sample now, and so now we can test it. Say what is our test statistics? So that's going to be where this formula right here comes into play at the bottom of the page here. So we've got p bar 1 minus p bar 2. And so that's p bar Seattle minus p bar Minneapolis. So again, just like in our confidence interval, that's going to be negative 0.02. And then we've got to have something to divide that by in our denominator. Now, and this actually, and I should mention here too, right? So we're saying here we're not speculating in our statement that there's any difference between the population proportions, and so in that case, we just will say becomes a 0, right? So this is negative 0.02 minus 0. Okay. So, but in this case, from our hypothesis statements, we don't see any difference speculated there, and so therefore we can assume that to be 0. And then here, we'll work now on the denominator here. So that's where this p bar, this 0.34 value, comes into play. So here we've got the square root of 0.34 minus 0.66, okay? And we're going to multiply that times 1 over 200 plus 1 over 180. Okay? So far, so good. When we calculate that, that becomes the square root of 0.0024. Okay? And then that becomes, when we take the square root, we get 0.049. Okay, so again, this is going to be slightly less than half, 0.02 divided by 0.04. But so if we calculate that out, we get actually a negative 0.41. Okay. All right. So where that would fall then, so if in the center of our distribution here that's 0, negative 0.41 is somewhere on this side here, but it's not in the rejection region. It's greater than negative 2.575. So again, thinking back to where we were with this, we would say, okay, we took a sample, and we have two proportions. Seattle was less than Minneapolis, and so we're in the negative side of the distribution up here, as discussed, but we're negative 0.41 standard deviations below the mean, below the our distribution up here. And so we would say, well, yes, it's less, as our sample indicated. Seattle is less than Minneapolis, but it's not so much less that it falls into the rejection region, and we can conclude that Seattle is always less than Minneapolis. So very similar to our conclusion about the confidence interval, right? The confidence interval tells us the range of possibilities that might be true, and then the hypothesis test says at what point are we beyond that, where we would say we can conclude that that the proportions are different. And so in this case we can't, so we do not reject the null, and therefore so we have a consistent result with our with our confidence interval as you would expect. And so that's how we do both confidence intervals and hypothesis testing for comparing two proportions.